Hey there students, welcome to Psych63 Lab Module 10 where we'll be discussing meta-analyses and missing data. So if you couldn't tell already, there are two pretty different subjects that we're going to be talking about today. So essentially I'm going to encourage you to do part one, listen to the part one of the video and then do part one of the assignment. And then we'll do part two of the video and then do part two of the assignment. But we're going to go ahead and start off with what meta-analyses are and how to conduct them in R. So part one is meta-analyses. So overall, there's 9 steps that you need to do in order to perform a meta-analysis. These 9 steps are generally applicable to all meta-analyses. So first, you frame a question based on a theory. You run a search on a Google Scholar or PubMed. You read the abstracts and titles of the individual papers. Get the abstract information from the set of articles. Determine the quality of information from these articles. And this is done using judgment and internal validity, but also using something called grade criteria, which we're not going to learn about today. Determine the extent to which these articles are heterogeneous, estimate the summary effect size and odds ratios using both fixed and random effects models and construct a forest plot, determine the extent to which those articles have publication bias and run a funnel plot, and conduct subgroup analyses and meta regression to test if there are subsets of research that capture the summary effects. All of that to say, really, meta-analyses is a really broad topic and it takes a long time to perform. Today, we are only going to be doing steps 7 and 8. So just keep that in mind in the big picture of things, that we're only doing a small subsection of the entire process that it takes to perform a meta-analysis. So we'll just be estimating the summary effect size in the forms of odd ratios and using both fixed and random effects models to construct a forest plot. And we're going to determine the extent to which these articles have publication bias and run a funnel plot today. That's all we're going to be doing today. So remember, we're only doing a small subsection of the entire concept of a meta-analysis. So let's go ahead and get started, and I'm going to have lessons throughout as well. So we're going to go and open up our RStudio. Then go ahead and create a new R project, new directory, new project. And we're going to do module _10. Make sure it's saved in that correct place. Create that project. There we go. So we've got it saved in the correct place. Let's go ahead and download the data set. So we're in the Module 10 lab, and it's the studies.csv. Go ahead and download that. As you can see, we only have 3 variables. I'll explain more of what these variables are in a later slide. Save as, browse it to our desktop, Psych63, Module 10, and it's just going to be called Studies. There we go. All right, and then let's go ahead and create a new notebook. Go ahead and bring this down. Delete the unnecessary text. Go ahead and name this meta-analyses. And then we'll go ahead and create a table of contents. USC:yes. And we'll go ahead and name this. We're going to be creating 2 notebooks today, so I'm going to name this module and notebook. And I'll name it meta for meta-analyses. Save that. Okay, let's go and see what we got next. So we've gone ahead and downloaded our project and downloaded the studies.csv. So next thing we're going to do, we're going to be loading in 2 packages. We're going to be loading in the library tidyverse and in the meta package. So we'll be installing the meta package as well. And let me go ahead and just load up some notes here real quick. Okay, there we go. So we're going to use the library tidyverse and the meta package today. So do hashtag load libraries, insert a new R chunk. We're going to do install.packages meta. And we're going to do library meta library tidyverse. And we'll go ahead and play that. Installing the meta package. A little bit of time. There we go. It's loading up the meta package and the library tidyverse. There we go. I'm going to go ahead and hashtag out this install packages, and it's going to reload it to get rid of that output. There we go. Perfect. I'm going to go and save real quick. All right, so next thing we're gonna do, we're gonna go ahead and load in the studies.csv file too. And we're gonna name it into a new object called study. So hashtag read in data. So insert in our chunk. We're gonna name the studies. Then assignment operator read underscore CSV quote studies.csv. Okay, and then we'll go ahead and load that up. All right, so this is our data set. We have 20 observations. We have an R value, an N value, and a study value. And I believe on the next slide I explain what these are. So just imagine that we did a meta-analysis. We did all those steps before, and we came up with 20 different studies. And essentially, from those studies, we collected the study effect size, which is correlations in this instance, the study sample size for each study, and then the study name. So imagine this S1 was something like Yates et al. 2003 or something like that. For now, we're just using S1, S2, and so forth. But just take that into consideration. So we have the correlation for each study. Each row is its own study, the N for each study, and then the study name as well. And we're going to be using these to perform a meta-analysis on the studies in order to establish some sort of pooled effect size and see how different these studies are. So to do that, we use the metacore function from the meta package. And what we're going to be doing is comparing the correlations across all these different studies. And what I've done is I've labeled everything for this. So we're going to name a new object. We're going to name it MA for meta-analysis. Use an assignment operator. We use the metacore function saying that we're going to do a meta-analysis with correlations on our things. We have a core equals, which is a column that indicates where the correlations are placed, which is in our R column, which is just different correlations for 20 different studies. Then we indicate where the sample size is indicated, which is the N column. So here we have the N column, so we sample the sample size for that. And then we do the stud lab, which is the column where the names are placed, and we have that in a variable called study with a capital S. And then we simply indicate the data set that we're using, and then we print out the object. So let's go ahead and see what that looks like, okay? So we are going to go back to R, go back there, and use the metacore function. So we'll go ahead and bring this down a little bit more. There we go. Okay, so we're going to do hashtag compare the correlations across studies. Insert the new R chunk. We do MA, use an assignment operator. Then we use the metacore function. So then we do core equals R, comma, N equals N, because that's the name of the column in our study. Stud lab equals study with the capital S, comma, data equals studies. So again, correlation, we're grabbing the R, the correlation from here, then we're grabbing the N, which is the study sample size, and then we're grabbing the study name. And when we do that, and we go ahead and put in an object, and then we're just going to print out the MA object. Go and press play, and we get a series of correlations that for each of the studies, and it just simply spits out a lot of information here. And in the next slide, I explain to you what this information is. So what we've done is we have created a weight of the fixed effects and random effects models and saying, okay, how much weight should be added to this study based on the sample size and the correlation that was in there. So with the weight each study encompasses, so those with higher sample sizes get more of a weight. Next, we get in purple here, which is the weighted average correlation for both fixed and random effects models. So we say this is the average correlation across all the studies. So 0.2809 is the average correlation with 95% confidence intervals. And we're saying, is that different than 0, essentially? And saying, yes, it is. So the average correlation is different than 0. Then we get a percentage of total variability due to heterogeneity across studies. So essentially what this number is saying how different are these studies from each other? Do they come from the same population, essentially? And here it's actually rounded down to 0.0%. And we're saying, no, there's not that much heterogeneity in the study. Usually if you have a I-squared value above 30%, that's a bad thing, essentially. It's saying that there's a lot of heterogeneity within this. And then we have the Cochrane's Q, which is located here, which is the sum squared deviations of the effect size estimates from the overall mean value. So a significant value is an indicator of heterogeneity, which is not good. So here we actually pass our heterogeneity test and saying, okay, yeah, essentially there isn't heterogeneity within our studies. And what we're able to say is that these studies are similar enough that we can run these correlations against them. If this was a significant value, then you'd be saying, oh no, our studies are way different from each other. There's something wrong with our studies, essentially. So you're hoping that it's not a significant value. And your I-squared value is an effect size that you're hoping is lower than 30%. It's kind of the general consensus. So we've gone ahead and done that. Then this is probably like the real meat of what your output is, essentially. So you can see, again, just to run over again, you have the study, what the correlation for each of those studies were, the 95% confidence intervals based on those, which is used from the end, the weight from each study, when the fixed and the random effects weights, and based on what the sample size is will determine whether it has more of a weight than a smaller sample size. You get the fixed and random effects models and the average correlation, the I-squared, which is the heterogeneity. You're hoping that that's less than 30%, and then the test of heterogeneity, which is the Cochrane's Q. So the next thing we're going to do is we're going to plot a forest plot, actually. And it's pretty simple. The meta package makes it really simple for us. You simply do forest, and then you input the meta object that you just created, which is the MA object that we just created. So let's go ahead and create a forest plot. Hashtag create a forest plot. So we go ahead and insert a new R chunk. And the way we do that is simply do forest, and then we're just going to input our MA object, which is our MA object. We simply do that. It's just a nice looking plot of what we did. As you can see, we have the average, the summation of the thing here. I'm going to do something real quick and do fig.width equals 8 to make it a little bit nicer for us. There we go. So we have everything there. So there's a pretty big thing, but as you can see, it really just made this. It just made this look a lot nicer for us, and we get some nice visuals as well. And we see the correlations, and we see the summation correlation here as well, and say, okay, yeah, so we have this average correlation, which is 0.28, and all the correlations too with their 95% confidence interval band, seeing where they cross in the weighted correlations here. So our average correlation is 0.28 across all of the studies. And you can see that these are all relatively similar studies saying, yeah, it's all very feasible that the 95% confidence intervals for each of them contains the overall correlation effect size for this. So we went ahead and we created a forest plot. The next thing we're going to do is we're going to go ahead and create this is what it looks like essentially. The next thing we're going to do is create a funnel plot here. So we're going to do hashtag create a funnel plot, insert a new R chunk, and all we do is funnel, and then the name of our meta-analysis object that we created earlier. And then we simply run that. And then what we get is a funnel plot. So as you recall from Kevin's lecture, essentially what we're looking for is saying, hey, is this a symmetrical, and does this look symmetrical? And essentially saying if there's asymmetry, it means that there's publication bias. If it's symmetrical, which this one does look somewhat symmetrical, saying that, okay, yeah, we have about the same amount of studies on the left side as the right side of this kind of pyramid looking structure. And we're saying essentially that there's not publication bias, or at least no foreseen publication bias, because we have a symmetrical funnel plot, is what we're saying. So it's plotted all of your studies and saying, okay, what's the chance that we have publication bias from our funnel plot? And that's what you're looking for, essentially saying, is this have publication bias associated with it? So that's really all we have to the meta-analysis section. I have some notes. So essentially, the meta package allows you to run way more meta-analysis than just comparing the correlation across studies. We don't have enough time to go through all the lessons that you can do, but you can compare different effect sizes such as odds ratios, which would be the meta-bend function, or Cohen's D's values, which would be the meta-cont function, and even more effect sizes that you can compare across studies. To read more on the meta package, I gave you the vignette here so you can read more on it. Okay, so this is the part where I'm going to say you should go ahead and pause the video and go ahead and start part one of the assignment, which is meta-analyses, and then we'll go ahead and continue on to handling missing data next. All right, students, welcome to part two, in which we're going to talk about handling missing data. So up until now, all of our data sets have been completely full. There's no missing data in any of them. So now today we're actually going to be working with a data set that has missing data. And essentially, missing data are observations that should be part of your data but simply aren't. So in this example, you have ID number 4, which has missing data on Y, X1, X2, and X3. And what we're going to be doing, and we're going to be using a different method for handling missing data. Let it be known that there's a lot of different types of missing data, ways of handling missing data. For R, by default, uses list-wise deletion by default, which can make you lose a lot of power and or lose biased results. What we're going to be learning today is multiple imputation by chained equations, otherwise known as MICE for short, in which we're going to be using imputations to substitute the missing data with estimated values. So it's a little bit different than listwise. It doesn't just delete the case. Instead, we're going to be imputing actual numbers that are estimated for the estimated values. So for this demo today, what we're going to simply do is run a simple linear regression using pairwise deletion, which is the default in R. Then we're going to impute data sets missing values using the MICE package. Then we're going to run a simple linear regression in the imputed data. And then we're going to compare the model estimates across the missing data techniques. See, does it really differ that much between pairwise deletion and the MICE missing data technique? So let's go ahead and go back into R. What we're going to do is we're going to go ahead and go to desktop, Psych63, module 10. And we're going to go ahead and open up that project file. All right, it's taking a little while to load. There we go. And then we're going to go ahead and download the data set. So we'll be doing the mice data1.csv. Download that. And go ahead and save it into our correct file path. File, save as, browse, desktop, Psych63, module 10. I'm going to remove this one. Oh, it looks like I already have it saved in, but it should work out the same. Yes. There we go. Go ahead and got our, and then let's go ahead and create our R notebook. Okay, delete the unnecessary text. We'll use this missing data notebook. Okay, create that table of contents, yes. And let's go ahead and save our notebook. So we'll go ahead and name this module 10 notebook, and then missing data. There we go. All right, we'll go ahead and save that. Let's see what we got next on our slideshow here. So we got that. We download the MICEdata1.csv from Canvas. Okay, we're going to go ahead and open up three new libraries. The three libraries today. We're going to use the tidyverse package, the MICE package, and the OLSRR package. Let me just go ahead and load up some notes here real quick. There we go. Let's get back up there. That would be perfect. Okay, so let's go ahead and do #load libraries. Yeah, I cannot spell. There we go. Insert a new R chunk. So we're going to do library. So we're actually going to do install.packages. And we're going to first load up the MICE package, because I don't believe you've used that at all. And then do library, tidyverse, library, MICE, and library, OLSRR. Go ahead and run that. And install the MICE package. Give it some time. Perfect. There we go. Loading in the tidyverse package. There we go. OLSR and MICE. There we go. Go ahead and hashtag this out. Go ahead and press play. Get rid of it. There we go. Perfect. So what we got next? All right, next thing we're going to do is we're going to go ahead and load in the data that we're going to be using. We're going to name it mice underscore data 1. So read in data, insert a new R chunk. We're going to do mice underscore data 1. Use an assignment operator, read underscore CSV, quotation marks, and be mice underscore data 1.csv. Go ahead and press play. Perfect. So as you can see, we have X1 and X2 that we're simply going to be working with. It's a pretty small data set with 440 observations. And as you can see, there's randomly missing values within X1 that we'll be working with today. And that's essentially what I'm representing here, saying that X1 has some missing data associated with it. So the first thing we're going to do, we're just going to do a simple linear regression in which we regress X1 onto X2. So let's go ahead and do that real quick, okay? So let's go ahead and go back to R. So we're going to do hashtag regress X1 on X2 period X1 has missing data. And then I'll do colon list-wise deletion. Okay, let's go ahead and bring this down a little bit. Insert in our chunk. And we're going to name this mod1, use an assignment operator. We're going to use the lm function, and we're going to do x1 regressed on x2, comma, data equals mice data 1. And then we can go ahead and do OLS underscore regress mod1. Play that. This isn't really this is just a simulated data set, so we're not really focused on significance or anything. We're just focused on how it's handling the missing data. So by default, what R does is uses list-wise deletion. It says if that value is missing, then I simply delete it and can't use it at all. That's simply what's going on. But as you can see, we don't have a significant model with this data, but then what we're going to be doing next is we're going to be going through the process of imputing missing data. So this is just what it looks like when it's a list-wise deletion. We're going to go through the process now of going and essentially filling in these values with the best estimate values using the mice package. So we went and did that. So we interpret the output as usual, and right up we'd say missing data was handled with pairwise deletion, essentially. And then we're going to go ahead and use the mice package to go ahead and do this. So what's going on is essentially we're going to use this function called mice, which is going to take in a data set, which is the name of the data set that you're imputing. M is the number of imputations, the number of imputed versions. So we're going to have 5 imputed versions. So that simply means it's going to try to take 5 guesses at what the best value is. Maximum iterations is usually is how many iterations we want of each set. Method equals PMM means predictive mean matching. That's the type of method we're going to use that. And then seed is just setting a seed, set.seed. We're setting our seed to 500 so that we get the same results every single time, essentially. That seed part isn't necessary, but it's just so we all get the same results across this. So what we'll do is we'll go ahead and do hashtag use mice for predictive mean matching on missing data. We insert a new R chunk. So this is going to create, so we're just going to name this imputed underscore data, use an assignment operator. We're going to use the mice function. We're going to specify our data set for the first argument, mice data 1, comma, m equals 5, so that means it's going to do this 5 total times. Max it equals 50, so we're going to iterate it 50 times. Method equal, in quotations, PMM, comma to that's that predictive mean matching, and then seed equals 500, so that we get the same results every single time. So this is going to create a lot of output, okay? So just a warning, you're going to get a lot of output on this. So go ahead and run that. And it's running through each of these. So it's iteration 1, and it does it 5 times. Iteration 2, it does it 5 times, and then it's going to do it 50 times. So it's going to take a little while to run. But essentially, what's going on is mice is using all the other variables to predict each missing value. So it's using variables from x1 and x2 to predict missing values. So it's going through these iterations. It's going to be a lot of output here, but as you can see, it's saying, okay, what is going to be the missing values for each of these? So it's saying it's running through. We're almost done here. We're at 47, 48, or 950, which is the last one. So it created a lot of output. Okay, but that's essentially what it is. It's doing its thing. And what we get is this new list that we're going to be able to perform regression analyses on using functions from the mice package. So let's go and do this next. So the next thing we're going to do is run the same simple linear regression of x1 on x2, but this time we're going to use the imputed data set. So we use something called the width function, in which case we use the width and you indicate the data set that you want it to work with, which is the imputed data set, which is that list that we did, the exp equals expression, in which we say use the lm x1 to regress on x2, and then we simply take a summary of it. So let's go ahead and do that. Let me get down to my notes here. Okay, so we're going to name this mod.imp. So we go to do. So let's see what I wrote here. So regress x1 on x2 for imputed data set. Insert a new R chunk. So let's see what we name this. And it mod.imp, not imp. Use that. Okay, and we use width, which is the function that we're going to be using, which is the width function. Use imputed underscore data, which is this data set, the one that we just did, that has it's a list of things. It's not really useful right now, but we're gonna be using this width function in order to make it so that it's interpretable output. Then we use exp for expression equals, and then your lm, which is the linear model, x1 regressed on x2. Then we simply do a summary of our mod.imp. And what it's going to do is it's going to give us, it's going to give us 5 different models in which it says, hey, here's for the first one that I did, here's the regression that we did. So it says, okay, we took 440 observations, and then this is what the first result is. Then we took it again, and we did it 5 times for you. We said, hey, okay, we did this with 50 iterations each, and we indicated data. So here's your intercept, and here's your coefficients. So it's saying, our predicted intercept with the missing data, using the predictive mean matching method, are these values here. So our intercept is 1.80, and then our slope for x2 is negative 1.1. So for every 1 unit increase in x2, we see a negative 0.002 decrease in x1, essentially, is what we're saying. And then the same thing for intercept here, and then here. So remember, it did 50 iterations of 5 sets of data. So we did it 5 times for 50 iterations of trying to get the best method of predictive mean matching here. So let's go ahead and see what we do next. I think the next thing is going to do is we're going to combine it all. So this is just where I simply say this is imputation 1, this is imputation 2, this is imputation 3, this is imputation 4, and this is imputation 5. So next, what we're going to do is we're going to go ahead and pool all the model estimates together to see what we can get here. So what we use is this function called pool, in which we just simply pool those 5 linear regression models together and say what is the average intercept and estimate coefficient for each of them. So we do combine. So we're going to name this combined imp, and then we're going to use the pool function to pool all of that data together, essentially. So we'll go on back to R, do hashtag pool model estimates across imputed versions of the data set. So we do insert a new R chunk. Let me just see what I named this. So I named it combined underscore imp. Use an assignment operator. So we use the pool function, pool fit, or pool should be pool mod.imp, which is that large thing that we just created, mod.imp, and then we do simply a summary of combined underscore imp. So what we're going to do is we're going to pool all of these estimates together into one regression analysis. There we go. So on average, with the imputed data, we have an intercept is 1.83. So when x2 is 0, x1 is expected to be 1.83. And then our x2 is saying for every 1 unit increase in x2, we see a negative 0.01. We see a 0.01 decrease in x1, essentially, for every 1 unit increase in x2. And it's not a significant p-value, which was to be expected. That's kind of what we thought of before. And so that's pretty much it okay, and then we can compare our results here and say they're not too much different, honestly, but they didn't really have too much different results. But if you have a lot of missing data, then it will make a difference in this. And then the pairwise deletion has the ability to bias your results, whereas the multiple imputation method has less desire to bias your data. So MICE is a really great way for dealing with missing data, and you can work on this with bigger data sets too, and it'll work out just as fine. So a few notes on the MICE package. The with and the pool functions allow you to pool model estimates for many common analysis. So in general, you should examine missing data patterns before using MICE. This can take MICE takes a lot of computational power and can take a long time to run in larger data sets. And additionally, it's not currently compatible with machine learning and some multivariate analysis. If you want to get in that, I'd recommend getting more into MPlus because it has more codes for multiple imputations. And then I give you the vignette for the MICE package here as well. So if you want to read up more, because there's a lot more functionalities associated with the MICE package as well. And that's pretty much it, everybody. Go ahead and get started on your assignment. Let me know if you have any questions. Thank you.